I would like to give two announcements. The first thing is your mid-exam will be reconducted in CIC only. Okay, so either best of two or otherwise whatever the upcoming exam that would be finalized. That so far we have not taken any decision. Okay, so everyone should attend that exam. Whoever are staying in the campus as well as whoever are outside. Okay, through the Moodle. Then you have to upload all the things through the Moodle and you have to submit your rough sheets also in the exam hall itself. Our all 8 TAs will be there in the exam hall. So that is regarding mid-exam. The regarding end exam also, just now I have posted one picture in our Teams itself. Just 5 minutes ago, I have received this mail from the institute. Whatever the final exams will be there, starting from 7th April to whatever 13th April, those exams also will be conducting through the offline only. Okay, so whatever date will be extending, starting from 7th to 19th like that, in view of accommodating all the subjects. Okay. This is regarding examination schedule. Okay, so now let us move to our subject. Do you have any doubts or questions regarding the examination? Quickly in 2 minutes, if you have any doubts. Okay. Okay. If no doubts, yeah, please.
Sir, how many tests we are having in this course?
This is only whatever the exam reconducting, that is the mid-exam. Mid-exam we are reconducting. So when final exam.
Only 2 exams.
Only 2 exams. Only 2 exams. Then where is the scope to take another exam also? Anyhow, you are attending on 16th. Then your end exam will be starting somewhere between 7th to 19th. If there will be one more exam in between, there is no scope to discuss. Even we have one holiday on the Friday. Friday actually that is big loss for us. We are losing 2 classes. Okay, so we have to cover all the syllabus since this is the central examination system. Okay, so that's what let's do our best. Any question or shall I move to the topic? Okay, fine, thank you. Don't worry about that. Only thing is you have to practice very well, because whenever you are attending the exam from your room or home, that is kind of open book exam. Nobody asking you to open the book. At the same time, nobody asking you to don't open the book. Okay, that is up to you. You use it to open the book and you use it to solve the problem. But in case of this offline exam, you will be coming to the examination hall. Okay, while coming, you will not bring any book, obviously. Yes, so that's what you have to remember all the relations. Okay, and you have to think about the concept, then you have to implement. Earlier, you might have opened my presentations also when you are answering the questions. Now you cannot bring those all the things. But anyhow, internet will be working. That I don't know how we'll be handling these all if you. Okay, so you will be writing in the series. Pardon.
For the final examination, the exams,
Uh-huh.
which are going to be offline. So for that, we won't be able to use like EES and stuff, right? We'll have to use the tables.
That I don't know. I think so. You will have to write the exam in CIC only. I think so. I think so. That
Okay.
I'll confirm it. Okay, I'll let you know. I'll let you know. So as of now, your mid exam is in CIC. Okay. So these many computer. Yeah.
Sir, in CIC, will we be provided with the tables, or like can we use ES, like how to get the property data?
So you can use ES, right? You can use ES. Okay. If you write ES, I think ES also will be installed on every computer. Okay. So then if it is that case, tables will be given to you. Already tables actually, one mail I have forwarded, which Professor Supranshu Roy has forwarded me. Okay, but anyhow, tables are available at the end of every book.
Yes, sir. Basically, when we are going to CIC, we cannot take anything with us, right? So
Yeah, you cannot take, but yeah, I'll let you know by evening today itself.
okay, sir.
I'll let you know by today. Yeah. Okay. So don't worry, but start reading the book again, our presentations, and try to understand and try to remember certain equations. Okay, once you understand the concept very well, then it is not difficult to remember the equations. Okay, so okay, let's move now. So what we have done in our previous class, we have discussed about entropy, and then we have solved some problems. Okay, the next to the entropy chapter is applying this second law of thermodynamics to the control volume. Okay, so that is again continuation with first law, second law, and then entropy, and then that equation applying to the control volume. That would be actually little boredom kind of thing. To avoid that, I am shifting for this particular chapter. This is very interesting chapter and as well as bit lengthy chapter. Let us finish this chapter first. Then let us go back to the applying control volume concept, whatever is the second law application to the control volume, that let us discuss. Those concepts are actually not very well included in this present chapter. Okay, so let us discuss this. Today's topic is about power and refrigeration systems. However, the one thing you have to remember, here phase change is happening. Without phase change also, the power and refrigeration systems are there. Okay, that let us discuss next to this chapter. In this chapter, power and refrigeration systems with phase change. Okay. So the most important thing with phase change, what we have discussed many times, that is Rankine cycle, which we are using in case of thermal power plants operating upon steam. Okay, operating upon the steam. Suppose you over here, the few times we have discussed about this also. What are the major components in case of Rankine cycle means? This is the boiler. Okay, here the water is heating to a high temperature and high pressure. In this case, actually, the water is taking the phase change, and that is at the steam. That steam is impinging upon the turbine. Okay, here this is the isentropic expansion we have considered many times. Here we are getting certain shaft power that we can call it as work. Okay, so then the exit of the turbine is saturated liquid or slight amount of moisture also would be there. Okay, sorry, saturated vapor, slight amount of liquid also would be there. This saturated vapor is passing through the condenser. The purpose of condenser is to change the phase again. Since the exit of the turbine is saturated vapor, okay, that is coming over here. Certain amount of heat rejection is happening over here. Okay, let us assume it is completely changed to the liquid phase. That liquid is pumping to the high pressure again. Where the pressure difference is coming? In the turbine, we are using a word isentropic expansion. Expansion means pressure decreasing. Okay, the same amount of pressure we have to supply to the fluid. So that's whatever the condenser fluid is there, that is the saturated liquid, is pumping to the boiler by using certain pump. These are the components and the working philosophy of the cycle. Okay. The same thing we can see in this cycle also. This is the TS diagram. This is the PV diagram. Okay. The here in the boiler is like constant pressure heat addition. This is when you want to compare this particular process in terms of second law of thermodynamics. This is the heat supply. This is the heat rejection. Okay. This is the heat supply. This is the heat rejection. This is the work output. This is the work input. The total thing is like net work output, because turbine is taking means giving you so much of the work. Okay, the net work output Q1 minus Q2 equal to net work output. That way you can relate this particular cycle with your second law of thermodynamics. Okay, fine. Let us see all the process. Here in case of the boiler, the process is constant pressure heat addition. Okay, that is the reason this is the constant pressure line. Okay, this is the constant pressure line. This is the subcooling. This is the saturated liquid. Here, whatever the heat we are supplying, that is the latent heat. Okay, this is the phase change process. This is the saturated vapor, and this we can call it as superheating. Okay, why superheating is required, and those are, let us see in the further slides. Now, this total process 2, 2 dash, 3, 3 dash. This total process is happening in boiler. Now, 3 dash to 4 dash or 3 to 4, whatever. Okay, so this is happening in case of the turbine. That is isentropic expansion. Since isentropic, we are saying entropy change should be 0. That's what this is, a straight line. Okay, fine. Also, we are calling it as the expansion process. That's what from here to here. Okay, this is the high pressure line. This is the low pressure line. Okay, so we are expanding. Then it is reached to the condenser. Condenser is again constant pressure heat rejection process. That's what this is, again one constant pressure line. Okay, one constant pressure line. This is the heat rejection process, and here actually phase change is happening over here. Okay, phase change is happening. That's what, whatever the latent heat is there, that is removing over here by certain other fluid actually. That is a condenser fluid we can call. In one of our example, we have seen certain amount of water is circulating in the condenser. Yes. Then this straight line 1 to 2, 1 to 2. This small straight line is isentropic compression by using pump. Okay. So these all process again we have plotted upon PV diagram also. Okay. Fine. Now once you see over here, this is the total thing. What we can call this A, 2, 2 dash, 3, 3 dash, C, B, A. This is like heat addition. Yes, heat addition means Q1 or QH you can consider in view of your second law of thermodynamics. This is the green one, like 1, 4 dash, C, A, 1. Okay, this we can consider heat rejection. Okay, then heat supply minus heat rejection, obviously this inside. Yes, this is our work output. Okay, then efficiency also we have defined very well many times, that is work output by total heat supply. Okay, that means the area in the curve of this yellow divided by area in the curve of this red. Okay, that is giving you efficiency. Fine. Now we have to analyze this cycle, okay, in view of how to improve the thermal efficiency of the system. Okay, how would you improve thermal efficiency of the system? There is one possibility. Keeping Q as the constant, increase the work output. Okay, increase the work output. Since Q is the constant, how would you increase the work output? You will be reducing this amount, the green. Okay, this amount. That is. How should we do those all the things? There are two possibilities actually. Here, if you see, the first possibility is increasing the steam temperature. Okay, and second one is increasing the pressure. Okay, these are the possibilities we have. Let us see here. The first thing is actually, once you compare over here, this red color, whatever I have given you dotted. Okay, what is happening over here? This is saturated vapor. Okay, saturated vapor. When you pass this saturated vapor to the turbine, whatever isentropic expansion is taking place, at the end, what is happening? This huge amount of moisture is there in that. Okay, huge amount of moisture is there. Then what will happen if huge amount of moisture is there? The turbine efficiency decreases. Okay, the expansion process not appropriate. That is anyhow minor issue. The major issue is turbine blades will be eroded. these droplets, whatever are there, the condensed liquid, these droplets are acting like high velocity, high momentum bullets kind of thing. Those are impinging upon the turbine blades, okay, and that turbine blades are eroding, okay, and surface finish will be damaging. In that case, the expansion process is not appropriate. The boundary layer problems will be coming. In fluid mechanics, you might have studied boundary layer concept and all. Yes. So that's what, when you are expanding upon the turbine at the exit, the moisture should not exceed 10%. Okay. Moisture should not exceed 10%. Okay. Then what should we do? The only way is increase the temperature of the steam. Okay. Then after saturated vapor, the constant pressure line is moving like this. Okay. That's what we have taken up to this. Then you expand it. Once you are expanding, then it is touching over here. Okay. It is touching over here in this pressure line. So here, what is the amount of saturated liquid here? Very small amount. Okay. That is negligible amount. Within this 10%. Then no problem. That is the reason we are heating the steam further to make it superheated steam. Okay. And also simultaneously, by keeping your percentage of moisture content at the exit of the turbine as the constant, once you are increasing this temperature, okay, then you can move more downstream. Yes, suppose see, if I have stopped over here, my superheating, if I have stopped over here, then once I start expanding, then this line will be touching over here. Okay. Then here, let us assume this quantity of saturated liquid at the exit is just 10%. Okay. Okay. Now, further superheating I have done. Then I am expanding. Here, whatever the percentage is there, that is just 2%, let us assume. Okay. Then in that case, what I can do? I can expand further up to this point. Okay. I can expand further up to this point. Then whatever this quantity is there, okay, that is 10%, let us assume. Then what happened? The work value, the yellow curve, okay, this yellow curve, I can bring up to here. Yes. Then this green curve is within this small region. Okay. Within this small region. That means once you are moving towards superheating condition of the steam, then you can allow the expansion process up to the lower pressures in the condenser. Okay. That way you can maximize the work output. You can minimize the heat losses. Okay. That is nice. But here the question is, but how long time you can increase the temperature? Okay. If you are keep on increasing the temperature of the steam, okay, do you think this turbine material will be sustaining? No, it cannot sustain. Why? Because if you observe, whatever the operating pressure is there, that you can convert in terms of stress. Okay. Stress. You might have studied in case of your first year mechanics. Yes. You might have seen over there the yielding curve. Okay. Yield stress curve. Like that, this pressure is obviously reflecting as the stress. High pressure means high stress. Okay. Then simultaneously temperature also you are increasing. The temperature effect is acting upon the material. If you go and search in the Google itself, with increasing the temperature, the yield strength of the material would be decreasing. Okay. That means, see, if the material is at the room temperature, you can apply so much of the load. If the material you have heated up to the red hot state means you might have seen in case of your forging. Yes. You are heating up to become red. 800 degrees centigrade. In case of mild steel, 700 or 800 in the range. Okay. Then what will happen? That actually when you are hitting by the hammer itself, that is changing its shape. That means that is the metal is very soft at that point. Okay. So in view of that, you cannot heat the steel beyond certain temperature. Okay. That will be affecting upon turbine material. Okay. So that is the reason. Here two possibilities are there. Look here. Maintaining pressure at the low. Okay. Maintaining pressure at the low. Low means relatively. And you are heating up to the high temperature, whatever. This is the constant temperature. Beyond this temperature line, you cannot go. Then what is happening over here? If you observe, this much amount of double hatching amount of work is increasing. Okay. Absolutely fine. The same time, this amount of heat rejection also increasing. 4 dash, 4 B, B dash. Work of 4 dash and 4, 3. Whatever this thing is there, right? Double dash, double hatching. That amount of work is increased. Simultaneously, heat rejection also increased. In this case, actually, you may or may not be getting the benefit of increased thermal efficiency. Okay. You may or may not be getting the benefit of increased thermal efficiency. Okay. Now let us see other possibility. Now I am taking it as high pressure. Okay. Since I am taking high pressure over here, at this point only, my maximum temperature condition is reached over here. Okay. Then I have started expanding. Then what is happening here? This much of single hatching amount of work is added. Okay. When you compare to this cycle, heat rejection also decreased. Okay. Heat rejection quantity is decreased. Then what can we conclude? Efficiency is obviously increased. Fine. Then what about dryness fraction over here? In case of this previous cycle of double hatching, it is obviously here at saturation liquid. Sorry, saturation vapor. Okay. And here in case of single hatching, when you have increased the pressure, what happened? Certain amount of dryness is noticed over here. Okay. In case of this double hatching, you are allowed to expand further downstream actually, till reaching the moisture content of certain limit. That way again, work may be increasing. Okay. But amount of heat rejection also slightly increased. That means what? No solution is giving you much benefit. Okay. No solution. In this case, heat rejection quantity also increasing along with the work. In this case, work is increasing, but we cannot expand to the lower pressures. Okay. Still, we have potential to expand lower pressures. We can extract so much of work, that potential we have. But in view of this particular moisture content, we cannot expand furthermore when you are adopting high pressure. Okay. Okay. Then what is the solution? Some solution is required right here. Some solution is required. Think about here, whatever here it is showing you, red circle. Think about. Can anyone suggest me something very quickly? Can anyone suggest me very quickly? No cycle is much benefit here. Whatever two processes we are believing here. Okay. And what shall we do?
Sir, if we continue from 3 dash to 3.
Means reaching up to here and continuing
Yes,
in the straight line.
Yes.
But what is the process you have here? We don't have such a process, right? Again, high temperature, constant pressure. Then we don't have such a process. We have these, means that is the addition of one more process in the cycle. We have 4 processes over here. Along with that, addition of another process here. Okay. So this itself is giving you an idea if you think. Okay, so okay, anyhow, I'm going to tell you that. What shall we do over here? Here we can consider a concept of a reheat cycle. Okay, reheat cycle. The same thing we are doing, whatever we have over here. We are adapting high pressure, fine. This much of work we are happily enjoying. And then, means how are we enjoying this much of work? We are expanding upon the turbine, but we are not expanding more down because that is creating the problem of moisture. We are expanding up to a certain point. Okay. Then, whatever the pressure curve here we have, upon the pressure curve, we are again heating and taking the steam up to here. Okay. Then again we are expanding upon another turbine. Okay, like this, like this. Here we have two turbines. This we can call it as high pressure turbine. This we can call it as low pressure turbine. Okay. So what are we doing here? In the boiler, we are heated this particular liquid to the high pressure and high temperature of whatever according to the material sustaining condition. That we are expanding upon this particular high pressure turbine. This means 3 to 4. Okay. Up to certain pressure, whatever this curve is there, this line. Then after exit of this particular high pressure turbine, that fluid is actually going back to the boiler, but not mixing with the boiler original fluid. Okay, this is separate. Okay, like a heat exchanger we can consider. Okay, going back to the boiler in the tubing itself. Forget about heat exchanger. You might be knowing or not knowing heat exchanger. Just going in the tubing itself. There it is picking so much of heat, but pressure is same. Then it is traveling from 4 to 5 like this. Okay. Then it is coming back to the low pressure turbine and expanding over. Okay. And this is also within the moisture content is within the limit. Here also moisture content within the limit. Okay. That way what we can do, the simultaneously we can move towards low pressure in the condenser side and we can maximize the work also. Heat losses we are minimized. We have maximized the work also. That way, reheating cycle we can use such philosophy. You can use many reheating cycles actually. Okay, even and one more thing actually. So what about pump side? Okay, what about pump side? This much of expansion you are doing, okay, to the lowest pressure, then you are pumping it. Okay, then boiler has to heat this much from this temperature to this temperature. Okay, that is subcooling process, whatever is there. So much amount of heat should be supplied over here. That is acting so much of load upon the boiler. Okay, is there any other idea which is giving you some solution over here? That is like regeneration. In the regeneration process, what are we doing over here? We are taking certain amount of, or otherwise we are trapping certain amount of, not trapping, tapping. Okay, tapping is different, trapping is different, right? Tapping means we are drawing some amount of, like your water tap. We are tapping some amount of steam over here. That steam we are mixing with this condensate liquid. Okay, such a amount of heat is added over here. That means this 2 to 3 heat is added in this process. Okay, this amount of 2 to 3 is added in this process. And anyhow, starting from this 4 to this point, saturated liquid point, this amount of heat is added in the boiler. Okay, that way also we can increase certain amount of the work. Okay, and we can minimize the heat losses. These are the two methods. And based upon certain equations we can form over here, what is the amount of steam we are tapping here, that is M6, okay, and what is liquid coming from the condenser, both are mixing and finally going to M3. That is the reason this M2 plus M6, okay, this is M2 coming after condenser, this is M2. We are writing this mass balance for this particular box, okay. M2 is coming from the condenser, M6 is amount of steam tapping from the turbine intermittently, both are mixing, that mass is equal to this, okay. Then obviously this mass multiplying by that enthalpy plus this mass multiplying by that enthalpy is equal to this mass multiplying by that enthalpy. This is your enthalpy equation, the mass equation and enthalpy equation, okay. Then here, how much amount of steam we are tapping, okay, that we are taking in terms of, we are taking one ratio as the y, that is M6 by M5, okay. That will be very small amount, okay. Then anyhow, in terms of this y also we have calculated in terms of enthalpy also. These all equations we will be using in our tutorial, okay. Solving the problem for this particular is not new to you, okay. This is not new to you. We have solved these kind of cycles in our first law of thermodynamics time and second law of thermodynamics time very well by using our ES also. Same thing we will be using, and however these kind of other things are coming, okay. This much of heat addition, this much of heat rejection, what is the benefit, what is the efficiency enhancement, these all additional things will be adding, okay. Otherwise the problems would not be much difficult in this case, okay. This is a regenerative cycle. Some other regenerative cycles also there. Here actually what are we doing? Here we are directly mixing here, okay. Instead of directly mixing, there is certain fluid is not mixing but heat only transferring, okay. So that kind of facility is also there. That water, whatever in this heat exchange water, again feeding back. I'll show you detailed cycle like this, okay. This is a high pressure turbine, this is low pressure turbine. Why are we using these two? To adapt our reheating, okay, to adapt our reheating, okay. Now we are adapting over here these things. What is that? Tapping, okay, tapping. This tapping, we are tapping over here 1, 2, 3 locations and here one location, okay. Finally this is coming from the condensate, this is the condenser, okay. Here we have one more trap. What is the trap means, okay. Here this is separating, means this is allowing one fluid only, that means liquid, okay. This is allowing liquid only but not steam. That's what we called it as trap. This is tapping, this is trapping. That's what both the terms I'm specifically mentioning over here. This is the trapper, this is the tapper, okay. And this many amount of tappings we are doing and mixing over here. This is the feed water heater kind of thing, not direct mixing. This is the heat exchange type of, that whatever the liquid is there, that liquid again pumping back over here, okay. This is the actual thing whatever we see in case of our realistic thermal power plant. However, this regeneration whatever is there, right, this regeneration is not very worthy, okay. So why? Because however it is giving you certain enhancement in the thermal efficiency, you need to use many number of pumps over here, okay. If number of regenerators are increasing, number of pumps also increasing, okay. Simultaneously, if you are using feed water heaters kind of things, not directly mixing, then these units also adding, okay, and then trap units also adding. What does it mean? Means maintenance and operation is increasing. Along with that, initial investment also increasing, okay. Along with that, initial investment also increases. But however, what is advantage of using this reheating and regenerator means, upon same thermal power plant of certain one unit, you will be able to maximize the production. Okay. If you don't use these kind of things, you may need to establish two units in the same location. Okay. So that is about what is the Rankine power cycle, what are the processes involved in that, okay, and what are the methods to improve the thermal efficiency. Those are like reheating and regenerating, okay, that we have seen. And whatever this Rankine cycle is there, that whatever this blue color is showing you, that is ideal cycle. This particular image we have seen when we have discussed about entropy, and even that was questioned to you. Okay, so this 4 should be moved this side or that side. Yes, I have asked you that time. Yes, then entropy will be generating, it should be greater than or equal to 0. In that case, it should not be this side. If it is this side, that would be negative, but that is not possible. Yes, it should be greater than or equal to 0. It is 0, but actual cycle should be greater than. That is the reason point is here. Okay, so that is one thing that we have seen over there. This whatever dotted lines are there, this is representing actual processes involving when you are doing isentropic expansion and isentropic compression. Okay, the reasons are turbine losses and pump losses. Okay, turbine losses are like here what we are considering ideally adiabatic process. This isentropic process itself is adiabatic process. What does it mean by adiabatic? No heat transfer with the environment. Okay, but it is not possible actually. Okay, it is not possible. Okay, so certain amount of heat transfer is existing. That itself is one irreversibility. That itself is one irreversibility. Okay, the second thing is actually just now we have identified one point. If certain amount of moisture content is there, then turbine blades surface would be eroding. Okay. However, you will be taking so much of care about that. In certain cases, okay, so it could be happening. Then turbine blade slowly with the life will be changing, or otherwise, whatever the new blade system you have maintained, okay, in fluid mechanics you might have seen. Blade itself is one aerofoil profile. Yes, the turbine blade itself is one aerofoil profile. When you are arranging two blades in a stack, the gap between two blades is resembling like one nozzle kind of. Yes, one nozzle kind of profile. Because of that only the expansion is happening. Yes, because of that only expansion is happening. What is the reason we are keeping two turbine blades side by side means that aerofoil profile what is creating you, that is giving you in between the gap as the nozzle. Wherever nozzle is there, their expansion is happening. Now let us assume by certain reason of long time usage or otherwise erosions, okay, that certain distortions have been located over there. What will happen? And again, some amount of irreversibility is located over there. These are all irreversibilities, okay, is making this process as deviating this much. Okay, but certain way this is advantageous to us. What is happening? Moisture content is minimizing. However, and here in case pump losses, okay, similar. That's what these two are here actually. Okay, the next slide let us discuss about these two. So in this slide, why these two are at one point means the pump is also same, right? Isentropic compression and considering it as adiabatic process, That means heat loss is 0. Okay. The similar problems, whatever we have discussed, those also coming here. Okay. Now see here. This is ideal cycle. Whatever here, the lined one means solid line, and this dotted line one is actual cycle. These two we have discussed. Isentropic compression as well as isentropic expansion. What are the irreversibilities are involved? Because of the irreversibilities, this is deviating from this ideal line. Now what is happening over here? This is in the condenser. This is in the boiler. Okay. Again, see, from boiler to the turbine, it is passing through the tubes, is it? Or pipes, piping we can call, through the pipes. Then certain heat losses are there in the boiler itself. Okay. And also the piping. However, you will be insulating very well. Certain amount of heat losses will be existing. No perfect insulator is there in the world, is it? Which is giving you zero heat transfer. That's what in the piping itself, again, certain heat losses are there. And those pipes itself having certain frictional losses because some certain friction is there. Okay. So these kind of losses are common in case of your boiler as well as in case of your condenser. Because of that, combinedly, all irreversibilities together, making this ideal cycle as distorted like this actual cycle. Okay. That is about your completely about Rankine power cycle. Okay. Now let us discuss something about refrigeration cycles also. Refrigeration, as I initially I have mentioned, the power cycles. Even the IC engine cycle is also power cycle, which is giving you power. Okay. Like that, refrigeration cycles also. Phase change refrigeration cycle, phase change power cycle. Similar way, no phase change means single fluid. Same power cycles and refrigeration cycles also we have. In this part, we are discussing refrigeration systems with phase change. Okay. All refrigeration systems you have at your home are phase change refrigeration systems. Okay. That let us discuss in tomorrow's class. Okay. Thank you. Thanks a lot. If you have any doubts regarding these all, we still have 3 minutes of time. You can ask me. Okay. Okay, fine. If you don't have any doubts, thank you. I'll let you know about the exam policies by today evening.